Well, all of that I said last time, so I don't need to worry about saying it again. I also wanted to show you some new things. All right, so here I have nitroglycerin. Now, we all know that nitroglycerin is explosive, and you would never expect it to have a negative heat of formation, because what would it mean if this had a negative heat of formation? It would mean it was more stable than the elements that make it up, and that just doesn't make sense. Since nitroglycerin is very reactive, right? We know it's an explosive. We expect that its delta HF0 to be positive. And it is positive, okay? So what does that reaction, oh, by the way, this is a structure of nitroglycerin. So you could see, I don't know if you can see it that closely, but you could see that there's a lot of charges here. You've got positive charges on nitrogen. Nitrogen is really pretty electronegative. It doesn't really want a positive charge. And then you've got separation of charge here. So you've got, this is unstable. You've got positive formal charges on nitrogen. And then you have separation of plus and minus charges. And as you know, these charges want to be right on top of one another. So that's not a very stable situation. And the reaction whose delta H equals the delta HF0 for nitroglycerin is this. Form 1 mole of nitroglycerin, which has a formula of C3H5O9. Have you ever seen a formula like that? That's a pretty crazy formula. And it's a liquid. So in order to end up with 1 mole of that, you'd have to start with 3 carbon. That would be in the form of graphite, which if you look up here, that's the stable form of carbon, is graphite. Okay, not diamond. You wouldn't have to break up your mother's diamond ring or anything like that. Plus, let's see. Oh, let's see. Am I crazy? I think I'm crazy. Oh, it's on the next page here. 5 halves H2 gas, because hydrogen stable form is H2. 9 halves. We have to put these weird coefficients because we have to end up with 9 oxygens, all right? And then finally, 3 halves N2. Did I get all those right? I think so. And this reaction has a delta H equal to the heat of formation of nitroglycerin, and it is positive, which really makes sense that it's this. So it would be that the product, which is the nitroglycerin, is less stable than the elements that make it up. Okay. And another example would be if you formed sodium chloride. So if you look on the chart, you see that NaCl has a negative heat of formation. And what reaction has a delta H equal to the delta HF0 for sodium chloride? Well, you start with sodium, 1/2 Cl2, that is the stable form of chlorine, and you end up with NaCl, and this is quite different, right? This is a downhill process. This delta H0 is negative 411 plus whatever decimal places. So this is more stable. And of course, why is it more stable? Well, you've got these sodium ions. You know, you've got this array. I don't have to draw for you. This is freshman chemistry. But anyway, here I go drawing it. So you've got lots of ionic bonds. So you've got these plus charges and minus charges, and there is a strong attraction. And there's so many of these ionic bonds. And so this solid form is more stable than the elements that make it up. So the elements that, make something up can be lower in energy or higher in energy. But if it's a very reactive thing, like nitroglycerin, you would expect that it would have a higher energy than the elements that make it up. And if it's something very stable like sodium chloride, you'd expect it to be a lower energy. Okay. So I said, I'm telling you all this about delta HF zeros, and I told you that they're a really big deal. And the reason why they're a big deal is because they can be used, these heats of formation, to calculate heats of reaction for many, many, many reactions. Okay, so I'm going to show you how to do this. You've learned this already. This is using Hess's law, and this is something that students learn in general chemistry, although I often wonder how many of them actually understand this, So maybe if you didn't understand it so well back then, maybe you'll get it today. Maybe, I'm sure some of you really understand this, but where does this thing that we use all the time in chemistry, that delta H for a reaction is the sum of the heats of formation of the products minus the sum of the heats of formation of the reactant. So this is when we used in chemical reactions to get delta H zeros for those reactions, we say it's the sum of the delta HF zeros of the products minus the sum of the delta HF zeros of the reactants. And the question is, where does this come from? And I told you it has to do with Hess's law, but how does it have to do with Hess's law? So it has to do with choosing a very weird and crazy path of going from reactants to products. And the crazy path is taking the reactants. So this is the reaction that you want the delta H. You want this. This is the thing you want. Okay, so what we do is we, at least in our mind anyway, we undergo a two-step process. And step one is to break down the reactants to elements. What elements are they going to be? Well, they're going to be the elements that comprise all the reactants. And so you'll end up with elements in their stable form. And that's step one. So if you had hydrocarbons here, you would end up with carbon, hydrogen, and oxygen, all in their stable form. In the second step, it's a crazy path, like I told you. Step two is going to be to build up the products from these elements. And this we'll call delta H1, and it'll be standard. Everything is per mole. Actually, I don't know if I want to put the little zero there because it's more than 1 mole. Anyway, okay, so that's our crazy path. So we're going to get from here to here by taking this circuitous route. Okay, we're not going to go straight there, but it doesn't matter, right? Because enthalpy is a state function. So it doesn't matter how we go from reactants to products. It only matters that we get there. Okay, so the thing is, would you ever do this? Like in the lab? That's probably not. If you were going to synthesize something, You wouldn't take reactants and try to make elements out of them and then put those elements together and make the products. There are much better ways than that. That would probably be impossible. So I'm going to say no. I'm going to stick my neck out and say no. You really wouldn't do it this way. I mean, there's probably some very simple examples where you might. So you wouldn't do it that way. So I'm going to say no, but we don't care, right? You don't have to do it in the lab. We can just do it on paper. Of course, sometimes, somewhere, somebody will have had to, and it's taken generations, to accumulate all this data for heats of formation, which are gotten sometimes by doing those reactions, but sometimes by combining other reactions. So that's, the way the National Institutes for Standards and Technology gets that data. Well, that's kind of their problem. It's not really my problem. You know what I mean? You know what I mean, right? All right. Anyone who nods their head, I appreciate it. Okay. So delta H0 for this overall reaction is just going to equal delta H1 plus delta H2 for this crazy path. All right. Let's think about delta H2 first. Okay. Because delta H2 is actually pretty easy to picture. That's the second red arrow over here, all right, this one. And the reason why that's pretty easy to picture is because what you're doing is you're going from elements in their stable form to products. Well, when you go from an element in the elements in their stable form to something, those are heats of formation. Those are standard enthalpies of formation. So this is forming products from their elements. Okay, so this delta H2 is the sum of the delta HF zeros of all the products. And since you might have, say, 3 carbon dioxides or 2 waters or something, you have to take each one and multiply the delta HF0 for that thing by the stoichiometric coefficient. So it's the sum of the delta HF zeros of, I would say, each product multiplied by its stoichiometric coefficient.
Dr. Cooley, is it the delta HF of each product or each element in its stable form?
It's you would have let's say you ended up with 2 H2O and 2 CO2. You would have to have 2 delta HF0 of water plus 2 delta HF0 of CO2. So it's the stoichiometric coefficient multiplied by the heat of formation for that product. Okay, so the way we actually write it is we use a summation notation because that makes everything so much clearer, using summation notation. But just to explain to you, since you brought it up, which is a good question. So I call this, each of this is the ith product, right? So you sum over this product and this product. So this would be like I would be, let's say it could be H2O or it could be CO2. You have to add them all up. And this is the stoichiometric coefficient of each product times the delta HF0 of that product, right? So like I said, this would be the sum of these things if these were the products. And the new is used for stoichiometric coefficients. It's just what, that's what it's always, that's one of the many things it's used for in science. So that's the step that's pretty good because you're going from the elements here to the products. But we also have this other step, right? And look at that step. That is actually the reverse of going from the elements to compounds. That's going from compounds to the elements. Okay, so this step is the sum of the negative of the heats of formation of each reactant, right? Because the negative of a heat of formation would be making elements in their stable form from the compounds. So the delta H1 is going the opposite direction. Hold on, I'm having technical difficulties. I'm sure everyone understands because everyone has technical difficulties. I can't stand this, but whatever. Okay, let's go back. Okay, I know. See, computer's getting hot already. It's got a big workout tonight. So this delta H1 is going from compounds. So that by that I mean the reactants to elements in their stable form. So this is really the opposite thing. This is the sum of the negative of the delta HF zeros of the reactants. Multiplied by their stoichiometric coefficients. Okay, so just to give you an example, suppose our reactants were, C3H8O. Oh, somebody else is here. Hello. So suppose our reactants, what is this? This is a liquid propane, is that what no, it's propanol. C3, let's call it liquid, plus O2 gas. I don't know. Let's pretend. Let's make a number up. It doesn't matter. I just want to show you an example that, if this was the reactants and we're going to the elements, okay, so the delta H1 would be the sum of, okay, instead of it being the heat of formation of this, it would be the negative of the heat of formation of C3H8O. Let's put a 2 there just to make it interesting, because it would be -2. And then it would be -3 times the delta HF0 of O2, but of course that is equal to 0, but that's what it would be for whatever reactant it was. But this one so happens that the heat of formation is 0. So that's what I mean by the sum of the negative of the heats of formation of the reactants multiplied by their stoichiometric coefficients. So we would use, oh God, -2, no, we would say in general, the sum over I of nu I delta HF0 reactant I. So for each reactant, you would add the stoichiometric coefficient multiplied by its heat of formation. Okay, and that's why we end up with, when we add these together, excuse me, delta H2, we get delta H for the reaction, which is the sum of the stoichiometric coefficients times delta HF0 of the ith product. So we're adding each stoichiometric coefficient multiplied by its own heat of formation minus the sum delta HF0 of the reactant I. So that's why it's products minus reactants when you have, when you're using heats of formation. The reason is because as you go from reactants to products, this is a forward step for heat of formation. So this has positive heats of formation, and this has negative heats of formation because you're going the opposite direction of forming something from elements. You're forming the elements from the something. Okay, so now you know why it's products minus reactants. It's not final minus initial. That's not why it is. It's because of the, the exact, exactly what stepwise path we're using to get the delta H0 for the reaction using this method. So I'd just like to know, did everyone know that already? Or was that something did you learn that today? Well, what does the naughty mean? You knew it already or you learned it today?
I think I kind of knew it, but didn't really know it. I didn't understand it.
I tell my freshmen the same thing, but I don't know how many of them. I don't know what I knew when I finished freshman. I don't think I knew very much. But anyway, freshman chemistry was very strange for me because my first semester I had mononucleosis and I was sick for 3 weeks. And I dropped all my classes except for chemistry. And I just caught up on that one. But yeah, I don't think I knew much at the end of that course, I'll tell you. I got a B. All right, another way to figure out a heat of reaction is to use bond dissociation enthalpies. Okay, so we can also use bond dissociation enthalpies, which I talked about last time, or to calculate a delta H0 for a reaction in a sort of similar scheme. But there's a delta H, using heats of formation is a really great method. Those are all experimental values. You get very accurate delta H's for all kinds of reactions using heats of formation. There's a few more caveats to using bond dissociation enthalpies. First of all, these correspond to gas phase reactions. Like, for example, you can have H2 goes to 2H. You're breaking up. So that's the delta H for that would be the bond dissociation enthalpy for H2. This will give you this delta H is equal to delta H0 bond for H2. Okay, but that's for gas phase, right? And also this CH, there's no such molecule. So the bond dissociation enthalpy is an estimate. It's not really from a real reaction. So the thing is that it's best, this works best if it's used for gas phase reactions. I have to do that again. I'm going to try unplugging this. Oh, that's nice. Okay. So this works best for gas phase reactions, there was something else I was going to say, which I forgot now. Oh, the other thing is that you have to keep in mind that the best you can get is an estimate of the delta H0 for a reaction. And that's because they use averages of different bond dissociation enthalpies. Like for CH, they'd use an average of CHs in many different types of compounds. Okay, so if you keep that in mind, though, you really can use it to get a pretty good idea of a delta H and how it comes from the making and breaking of bonds. So here we have a reactant goes to products. I'm just going to say products, reactants. Go away. Thank you. Oh, hold on. And I'm going to use the crazy root, right? This is all about Hess's law. I'm going to use the crazy root that takes us through atoms in the gas phase. So it breaks down the reactants into atoms, builds up the atoms into products, and that's the kind of cycle. That's the path that we're going to use. So step one does that. It breaks the reactants breaks up into atoms, and then it forms products from atoms. So that's our pathway here, okay? And so let's think about this step one. Okay, so step one is breaking bonds. Breaking lots of bonds. Okay, so every time, all those bonds that you have to break, every molecule you have to break all the bonds. This is very endothermic, right? It requires energy to break bonds. If you had me, which I don't know if I had Isra, but maybe she's the only one. That's what I tell everyone in Gen Chem all the time. That's step one. So step one is going to be very positive, right? A very positive delta H for step one. And then we have step two. And step two is forming a lot of bonds. And that's going to be very exothermic. It's going to release a lot of energy. And so it's going to have a very negative value. Okay, so so what do you have to do here? Oh, hold on. Yeah. I somehow put all your email addresses in here. I don't know how I did that. That happened. That is bizarre. I don't know how that happened. Must have pasted. Must have been the last thing I copied. So what you're basically going to do is you're going to take the reactants. What happened there? Come on. Okay. And you're going to add up all the delta H0 bond, right? All the bond enthalpies for breaking all the bonds. And of course, then you're going to put a big positive sign on this, okay? Because it's very endothermic. And then you're going to, for the products, you're going to add up all the delta H0 bond for forming all the bonds. So that's going to be a very negative thing. You're going to add this all up. All right. So here's the thing. So this is going to be for delta H1 and for delta H2. So if it requires more energy, then it releases, breaking and forming all these bonds. Then the delta H0 for the reaction will be positive. If it requires less energy than it releases, then delta H0 reaction will be negative, okay? Okay. So, if you do that, you can actually look and see, oh, that's why the delta H is negative for this reaction. I broke, a couple of really strong double bonds that have very high bond enthalpies, and I only formed some weaker bonds here on the right side. So you can figure out things like that. And I tell you that when you do problems like this, sometimes, well, most of the time, I don't do it the way I just described. I would pick out which bonds. A lot of times in reactions, some bonds, you could just pretend they're left alone. They may actually break and reform, but if they're still there at the beginning and the end, you don't care. So sometimes it's easier to it's easier not to break up all the bonds, right? It's easier not to tear the whole molecule, all the molecules apart into atoms. Sometimes you just look and see which bonds break and which ones form. But I'm going to have to tell you that you have to really be careful here. Whenever I do a problem like this, I do it at least twice. And I'm telling you that the first 2 times, I usually get 2 different answers. So when you do a problem like this, don't just do it once. Start from scratch, count up the bonds, count up how many CH bonds broke, how many CC bonds broke, etc., how many blah, blah, blah bonds form, and add up all those delta H those bond enthalpies, and then do it again. And if you get the same answer, man, you're a better man than I am. but if you don't, you're just like me, and you need to do it a 3rd and maybe even a 4th time to make sure you don't make a mistake, because it's just very easy to miscount or to miss a bond. So do it 2 times and maybe more. Because usually that's all that's involved in that problem. Literally is you have to look at the right Lewis structures of these things. You have to know when there's a double bond, because that bond enthalpy chart has double bonds and triple bonds and single bonds. If you're going to do a triple bond, you don't take a single bond and multiply it by 3. You look for the triple bond on the chart. All right, every bond has a different entry on this. I should have actually. Well, anyway, I didn't get the chart. I think it's on assignment 3, has a bond enthalpy chart on it, I think. So you can see that. We're getting into some of the later problems from that assignment. Okay, so make sure that you don't miscount. That's one thing. Another thing is, please, it's positive on breaking bonds and negative for forming bonds. Students get this wrong all the time, so don't be one of them, okay? And I'm going to tell you that there are limitations. I already told you this, but there's more limitations even than what I said. So I said well, I'm going to tell you that these bond dissociation energies, that's what I call them, BDEs, are averages, right? I told you this already. So they will only lead to an estimate of delta H0. But there's some situations that are even worse than that. So often, and this should come as no surprise because you learn about molecular orbitals and things like that. I mean, bonds are just a model, and they're not that great a model for a lot of molecules. So oftentimes, a molecule is really not the sum of its bonds, right? So just two familiar examples. What's this, right? This is cyclopropane. So if you look up a CC bond here, you know, these are carbons, hydrogens. The CC bonds in cyclopropane, they're not as strong as regular CC bonds. This molecule is very strained. So this is actually, this molecule is less stable than bond dissociation energies would predict. Because after all, they're just taking into account ordinary bonds. So that's one, but of course, then there's the famous benzene, right? Which, you know, what are you going to do if you have a benzene ring and you're trying to add up bond dissociation enthalpies? You'll say it has 3 CC double bonds and 3 CC single bonds, okay? And for benzene is more stable than the bond dissociation energies would predict. Okay, so I would say that bonds are really a lousy model for benzene. And as you know, benzene has lots of nice looking molecular orbitals and you know, some of the lowest energy ones spreads out the electrons over all those 6 carbons, all that whole entire ring. So I'm talking about the pi system. Okay, so that's stuff that seems clear, but I'm going to tell you something else that's actually also very important, and that is that you really can't do this does not do a very good job of giving, and I really told you this already, but I'm going to be very explicit about it, of giving delta H's for reactions in solution. And that's because it's based on stuff happening in the gas phase, you know. Obviously reactions in solution, they're not getting the gas phase. And so you have to ask yourself, well, what's so different about a molecule in the gas phase versus a molecule in solution? Well, it could be lots of differences. There's a lot of charged particles in solution and things like that. But basically, what is not accounted for at all in this type of model, so there is no interactions between solute and, you know, solvent, and like, for example, water is included in any of this. Okay, so if you have reactants and products, if reactants and products interact strongly with water, or even more, if the reactants interact strongly, but the products don't interact in the same way, then really you'll have, you know, you won't be able to get a very good value. Okay. So these interactions influence stability. and they will affect delta H's for the reactions in solution. And bond dissociation enthalpies do not account for this at all. Okay, so not the best. So if you want to use bond dissociation enthalpies and get really good results, for best results, I think I said this already, for best results, gas phase. So that's pretty boring. You know, if you want a precise value, if you want an approximation, that's not a problem. And I would say no special characteristics like you know, resonance or all right, so that's what I have to say about that. And now some problems. Okay, so somebody's still writing. I don't know. All right, so there's a few problems that I'd like for us to work on. So is problem 1, and then there's problem 2. Which I'm adding something to. And then I believe there's a third problem as well. Okay, so this is what I'd like to do. I'd like to have you work on these for a bit. If you want to ask me a question, I'll tell you what to do. Send me a chat message or just say, hey, I'd like to ask you a question. And if you want to just talk to me, I'll open a breakout room, and we could go in there and I could explain something to you. But otherwise, I can just explain it to you, you know, so everyone can hear. But it's really up to you. You could send me a private message, you know, on chat, and I will see it. So I'd like you to work on some of these problems if you don't mind. Because I think everyone could use some practice, and there are some little ins and outs with these that, you know, I want to make sure you know how to do. If you don't know how to get started, send me a chat and I'll meet you in a breakout room. Does everyone know I emailed you this handout? So in case you're not able to see it here, you should have it in your email. You might note in problem 2, constant pressure and temperature, which I failed to write there.
Dr. Cooley, this is
Yeah,
might be dumb, but for problem 1, so it's a delta H of formation for O2. Is it not needed for this at all?
yeah, that the delta HF0 for O2.
Oh yeah, it's 0.
That's the trick question there. Yeah.
Okay.
So has anybody noticed that you don't have the heat of formation of liquid water, of gaseous water? You're not given that. Did anybody notice that you have the delta HF0 for liquid water, but not water as a gas? Because you can't just do the heats of formation of products minus the heats of some of the heats of formation of reactants here. Just want to, if anyone wants to ask me about that, I can talk to you about it. Israel, did you catch what I said? Or?
Yeah, I just realized that now before you said it, and I was
So
thinking.
I would recommend that what you might want to do is figure out what the delta H reaction would be for forming the liquid, right? And then you're given the heat of vaporization of water. So, right, that means water gas goes to water liquid. So you could combine that, right? So you'd have two equations that you could kind of add up together. but you have 3 moles of water. So, okay. I hope that helps some others of you as well.
Yeah, I'll try that. Thank you.
Quiet ones, the ones who don't show their videos or even their pictures. So I barely know what you look like if I were to run into you at the Stop and Shop. Just teasing. No.
I had that same answer.
You did? As Karen?
Yeah. Well, like once I went back and like, well, once you told like Israel like the whole thing with H vapor. And I messed
But
up.
what did you get for the first part? What did you get for, suppose you had this reaction?
I had a way lower number somehow. I had like -155.
Remember, I said that's a good idea to do this one with this being liquid. So what did you get for this reaction?
I had, I believe, I'll show you right now. Let me just go up my calculator. I had -155.
No, well, not 155. No, it's got to be 1,000 something.
Yeah, see,
155 something. What? 155.
0.08.
What?
0.08.
155.08?
Yeah, I messed it up somehow.
No, it's like 10 times bigger than that.
Let me see.
Karen, what did you get for that part?
Oh,
I figured out what I did wrong. I tried doing everything in one step, so I'm redoing it now.
Yeah.
Dr. Cooley.
Yeah.
So I realized like when I did it, when I kept it in liquid, I had like -2, but now that I like went back and just like fixed it, I got -1729.08.
For this reaction going to liquid?
Yeah.
No, it's not that. So it's 3 times the heat of formation of water right? Plus 2 minus 1 times the delta HF0, right? Is this what you used?
Wait, why on 2 of the CO2s?
It's got a coefficient of 2.
Oh yeah. Sorry. I was at the wrong side. Okay. Oh.
Is it negative 1648
You mean the whole thing or no?
for the go into liquid?
No, no. I don't know. Maybe I did it wrong. I don't think so. I've done it many times, 3 times.
No, we believe you, Dr. Cooley.
Yeah, I don't believe me anymore.
It's products minus reactants, right?
Yeah, I just made a mistake. Maybe you forgot about the ethane. I don't know.
Well, I'm gonna work on it still.
Yeah, work on it. Israel, what did you get for this one? Did you get this yet?
Okay. I almost got my answer. 1 second. I'm just
Yeah, that's okay.
calculator.
Dr. Cooley.
Yeah.
Is it negative 1437.77?
That's the final answer. That's right. Yeah.
All right.
But that's not the answer to what I'm looking for here,
Uh,
which is minus 1559.7. And then you have to take that and then you've got to take 3 liquid waters and go to 3 gaseous waters. And then if you add those up, you get the right reaction. So you have to then add the minus 1559.7. And this one, the delta H, is 3 times the delta H of vaporization, which is 3 times the 40.65.
95.
So then this ends up being the right reaction.
Okay.
Dr. Cooley, how did you get the negative 1559.7?
It's just 3 times negative 285.8 plus 2 times, right?
Yeah, that's what I did. I'm just not getting that. I'm off by 84.7.
Well, I don't know. And you added the 84.7 that you should have added?
Mm-hmm.
Because it seems like you're off.
No, I subtracted the 84.7.
You add it. Well, you subtract the negative. It's a negative, so you're adding.
But isn't it? Don't we take the positive of it because we're breaking it down into its element?
No, that's accounted for by this negative sign here.
Oh, okay.
So let me be very clear on that. 3 times minus 285.8 plus 2 times minus 393.5 minus 84.68. So this is the sum of the delta HF zeros of the products minus the sum of the delta HF zeros of the reactants. But there's only one, right? But you're still subtracting it, so you end up adding minus 1,5. Oh, sorry, whatever these numbers are. You have to make sure that you add this, negative,
So my question then is, because I guess I'm confused when we were talking about it earlier with like the delta H1 and the delta H2. For the delta H1, we were going to take the negative of the heat of formation, or
we end
use
up with
the
this
value in the
negative sign.
chart, and
That's
then
how you
subtract.
get this negative sign here.
Okay, so keep the value in the chart always.
Yeah.
Okay.
Don't go messing with the value in the chart. Yeah, you don't want to do that. Yeah. Well, I made a mistake here, so I don't know what this is. Oh, I know what it is. I didn't do these intermediate calculations. Well, now I got really a crazy answer. Yeah. So that's how you get this first number here. And this is 3 times the heat of vaporization. Okay.
Okay.
So how is it for everybody who didn't say a word? Dina, how are you doing?
I got the same thing for the first part.
You got the same answer.
Yeah, for the first part, the negative 15599.7.
Right. So then you have to add, you have to take the liquid and form the gas. And then since there's 3 of them, that's 3 times the heat of vaporization, right?
Mm-hmm.
And then you'd add that. So that's, yeah. And Jack, I know. Benjamin, how are you? And Yolanda? Doing okay?
Yeah.
Alexis, forgot about you. Yeah, good. Okay. All right. Okay. Let's go on to the next one. Here's the next problem. Now, I do want to say something about this problem. This is finding this delta H0 reaction is really pretty easy. It's just going to be the delta HF0 of N2O4. That's 1 times that, because there's a 1 in the equation, minus 2 times the delta HF0 of NO2. So it's just, the numbers are all given here.
Negative 57.
Yeah. Negative 57 point, wait a minute.
121.
It's funny because I was looking at this third problem, which ends up being negative 571. So I was on the wrong page. But that's okay. So it's negative 57.12. Did you get that?
Yeah, I got it.
All right, now, no, whatever. You should keep a second here, honestly. So anyway, this is kilojoules, right? Kilojoules but per what, right? So this is negative 57.12 kilojoules per 1 mole of N2O4. It's per whatever the stoichiometric coefficients are for each of the participants in the reaction. So, and this is important if you're asked to do any kind of quantitative calculating. So, so it's 57 in freshman chemistry, we would write it this way. We would say 2 NO2 plus, goes to 1 N2O4, and we put a colon, and we'd write delta H0 reaction equals negative 57.12 kilojoules. And we wouldn't say per mole here, because it's assumed that you know that this is per 1 mole of anything that has a stoichiometric coefficient of 1, and per 2 moles of anything that has a stoichiometric coefficient of 2. And then we teach them that you take this value, and that's per 1 mole of this and per 2 moles of NO2. So then if you're given an amount of NO2, you have to be careful to always use this, to not just say, oh, that's kilojoules per mole of anything in the equation. Well, that can't be right, because if you have negative 57 kilojoules per mole of N2O4, it's not per mole of NO2, because it's 2 moles of NO2, that you would get by reacting that 1 mole of N2O4, or vice versa. So you have to be careful about that, all right, if you're doing anything quantitative with, an amount of a reactant or product. So that's my mouthful there, and you can work on the rest of this. How would you get delta U 0? So this is kind of a memory thing, right? Going back to, this is, I actually don't memorize those equations that relate delta H and delta U. I always go back to the definition. H is U plus PV, delta H is delta U plus delta PV. And then I say, okay, here, the delta PV, I would say, well, these are all gases, right? So this is delta nRT. And then what's constant here? We run this reaction at constant, we say constant temperature. We know that means the same temperature before as after. So, so this is just RT delta N. So delta U is delta H minus RT delta N. But you got to figure out what delta N is. It's not so difficult if you're looking for the 0 one. I would recommend when you do problems like this, do the per mole first, and then at the end you can multiply by numbers of moles. But anyway, how do you do that? What is delta N here? And remember, this is the delta N per 1 mole of N2O4 or per 2 moles of NO2. So for every 2 moles of NO2 that react, how many moles of gas are lost in this reaction? 1, right? So delta N is -1. You lose 1. So that means you have to figure out, so delta U is delta H0 plus RT delta N. We know this already. This is 8.314. I'm just going to use kilojoules per mole Kelvin. 298, -1. Okay. And look what's going to happen here. Uh-oh, I did something wrong. Yeah, this is a negative. See, it's negative. All right. And the reason I know that, the reason I figured that out is because delta U is Q plus W. This is constant pressure. So this is delta H. All right. And I know that this reaction, is it an expansion or is it a compression? It's going from 2 moles of gas to 1 mole of gas. It's a compression. So work is being done on the system. So that means that this term is going to be positive, and it is with a negative value of delta N. Okay, so minus this is going to end up being positive, and it comes out to plus 2.48 kilojoules. So delta U0 is negative 57.12 kilojoules plus 2.48 kilojoules. So what would you say about this reaction? You know, it released a lot of heat. And a small amount of work was done on the system. This first step so the reaction released a lot of heat. This decreased the internal energy a lot because it lost a lot of Q. And a small amount of work was done on the system, which raised the internal energy a little. But the main show was the loss of heat. And delta, oops, what the heck is that? And delta U overall is positive. Now, I'm gonna end class because it's 5:25 and we have to resume here at 6 o'clock and we need to have a break, including me. But the next part of the problem, you know, you should do it. Do it for next time. And I'd like you to look at the other problem as well. Because they're all good examples. I'll go over this. I'll go over it next time. Anyway, I'm not collecting them or anything like that. But you know, these are all good problems that you should know how to do.
Before we leave, is the second part of that question 2, is it final answer negative 29.97?
Sorry, final answer for which part of the problem?
For the delta H reaction of 184 grams of NO2.
No. What did you get?
Negative 29.97.
Hold on.
I got a way more negative answer.
Yeah, me too. I got 100 something.
114.
Yeah, negative 114.2.
Jack, I think I know what you did.
It's like off by a factor of 4, so maybe it is you multiply by the moles.
It's probably off by a factor of 2, right?
No, but he said it was 20 something.
Yeah.
Yeah, I got the 4, like pretty much the 4 moles of NO2.
Well, let me just show you that part then.
Am I supposed to balance the equation after I find the moles for NO2?
No, you got to remember that the delta H is per 1 mole of.
Yeah, let me just show you because it's good. We have it. Right, so it's 184 grams is 4 moles, right?
Yeah.
Did you get that?
Yeah, I got that part. Yeah.
So then you multiply 4 moles by negative 57.12 per 2 moles of NO2, right? Because this is the amount of heat released for 2 moles of NO2.
Oh, I multiplied it by the 9.
The what?
I multiplied it by the delta H formation, like of that.
Oh, no.
Oh, you know what I did? Oh my God, never mind. I know what I did. I flipped them. Okay, all right. Yep, I
All right,
see.
so in that case, you could just do number 3 for next time.
Dr. Cooler, I did have a question.
Yeah, please.
You said, but the main show was the loss of heat, and then this is delta U positive.
Oh, negative. Sorry.
Okay. All right. Good. All right. Then I don't have a question.
My bad.
All right.
Yeah. Oh. All right. All right. I'm gonna. So the way I plan to. So at 6 o'clock. What am I gonna do? All right. I kind of don't. So. I probably have people in front of me here who've done all kinds of different amounts of work on error analysis, problem 2, problem 3, on the urea lab. And I'm not quite sure how I'm going to manage all that. I thought what I would do is, for those of you who have done very little studying on error analysis, I would spend a short time even going over that simple problem 2 on the error analysis problems. I could spend a little time on the problem 3, and then I was going to spend some time on the discussion items for urea. The error analysis for urea is very similar to the error analysis for problem 3. So I think if I were to do more on that problem 3, then I wouldn't have to go over it specifically for urea. So I don't know quite what to tell you. At 6 o'clock, I think I'm going to meet and I'm going to say, okay, actually, maybe I'll just ask you right now. Does anybody need me to go over problem 2? I hope everybody knows what I'm talking about, because I'm referring to the lab lectures that you're supposed to have watched all of them before tonight. I see somebody's laughing, so I don't know what that means. But yeah, maybe it would help to go over the answers to problem 2, like just go over it very quickly. You know, how you add absolute errors, and how, you know, when you're adding or subtracting, when you're multiplying and dividing, you add relative errors. I mean, I'm not going over it from the beginning, but I will go over that problem. Is anybody, just send me a chat, or wait a minute, what else can I do? I don't want to do a poll exactly. I just want to do it. I don't know how to do a poll. Reactions, there we go. Okay. So how about if you tell me your reaction? I could a thumbs up. I don't know, there's no thumbs down. All right, I'm just going to ask. Give me a thumbs up if you like if you want to do this. How many of you would like to go over problem 2? I don't know where I see those things. All right, there's at least 2 for going over problem 2. So I'm going to do that. I'm going to start with problem 2. So if you don't have any need to go over problem 2, then I wouldn't bother tuning in until about 20 minutes after 6. You see what I'm saying? Sorry, folks. It's not going to be like the people who did everything get to leave early. I can't do it in reverse. I would love to, but I can't. All right, so 6:20. And how many of you need help with problem 3? Get rid of, how do I clear that thing? Oh, God.
They clear on their own.
It did. Oh, okay. So how many would like to go over part? I mean, I don't want to do the whole thing for you because it is an assignment, but I don't mind doing a bunch of it. So how many want help with problem 3? All right, so then what I'm going to do is I'm going to, hopefully by 6:20, I'm going to work on problem 3. And then I still have other stuff that I could go over with you. Like, I think it's important to go over what should be in the discussion. And I was just going to go through that briefly for urea and answer any questions you have. And I'll probably be able to do that, I don't know, I'm guessing maybe 6:45. So that's kind of my plan. But you could always just poke, you know, go, ask to be admitted and see what we're up to. Does that sound good? All right, so I'll see you back here, those of you who need help with problem 2 at 6 o'clock. All right. Wait, oh gosh. Oh, I'm gonna have to send an email. I'll have to come back to Chem 405. I don't have a Zoom room for Chem 407. I never set it up. So we're gonna come back to this same place.
Are we just doing urea today, right?
What?
We're just working on the urea problems today, right?
I can't hear you. What did you say?
Are we just working on the urea labs today, right? No other labs?
No, no other labs.
All right. That's 6.
Hmm.